For generations, we have drawn the solar system the same way. The Sun stands at the center. Mercury races around it in just 88 days. Venus glows beneath thick clouds. Earth carries the only known life. Mars waits beneath its red dust. Beyond lie the giant worlds, Jupiter, Saturn, Uranus, and finally Neptune, the last major planet. For many people, that is where the solar system ends. Past Neptune, they imagine only empty darkness stretching endlessly toward the stars. It seems like a reasonable conclusion. After all, if Neptune is the farthest planet, surely it must also mark the edge of our cosmic neighborhood. But nature rarely conforms to our simplest assumptions. The truth is far stranger. The solar system does not end at Neptune. In fact, it does not even end with Pluto, once considered the ninth planet. Nor does it end at the distant Kuiper Belt, where countless icy worlds silently orbit the Sun. It does not even end with the immense Oort cloud, whose frozen bodies may extend nearly a light-year into space. These objects are still bound to the Sun by gravity. They remain members of our solar system, even at unimaginable distances. So where is the true boundary? Surprisingly, the answer depends on what we mean by the phrase the solar system. There are, in a sense, two different solar systems. The first is the gravitational solar system. It includes everything still held by the Sun's gravitational influence: planets, moons, asteroids, comets, the Kuiper Belt, the vast Oort cloud. Gravity weakens with distance, but it never truly disappears. The Sun continues exerting its pull across trillions of kilometers, reaching far beyond the planets we know. Yet there is another boundary, one that cannot be seen through a telescope, one that has nothing to do with gravity. This is the physical solar system. It is not defined by the Sun's gravitational reach, but by something far more dynamic: a continuous stream of charged particles flowing outward from the Sun every second of every day. Known as the solar wind, this invisible torrent races through space at speeds exceeding 1 million miles per hour. It carries magnetic fields, energy, radiation, and the influence of our star across billions of miles. As the solar wind expands, it creates an enormous protective bubble surrounding the Sun and everything inside it. This vast structure is known as the heliosphere. It is unlike any border we experience on Earth. There are no walls, no signs, no visible horizon. Instead, it is an invisible ocean of plasma constantly pushing against another invisible ocean, the thin gas and magnetic fields drifting between the stars. Where these two cosmic oceans collide, something extraordinary happens. The solar system encounters the galaxy itself. For decades, scientists could only imagine what that distant frontier might look like. No spacecraft had ever traveled far enough to reach it. No human-made object had entered that mysterious region. It remained one of the greatest unexplored frontiers in astronomy. Then, in 1977, humanity launched two identical explorers, Voyager 1 and Voyager 2. Originally designed to study the giant planets, neither spacecraft was expected to continue operating for more than a few years. Instead, they exceeded every expectation. They survived Jupiter. They crossed Saturn. Voyager 2 continued onward to Uranus and Neptune, becoming the only spacecraft ever to visit those distant worlds. Then both probes continued flying, year after year, decade after decade, leaving behind every planet, every known destination, every familiar landmark of the solar system. Today, nearly half a century after launch, the Voyager spacecraft remain the most distant human-made objects ever created. Even traveling at extraordinary speeds, they move only a tiny fraction of the distance to the nearest star. The universe is simply that vast. Yet before reaching interstellar space, Voyager encountered something no one had ever witnessed before: the edge of the Sun's invisible kingdom. Scientists expected conditions there to become quieter, colder, perhaps even emptier. Instead, the spacecraft detected signs of increasing turbulence. Magnetic fields twisted into unfamiliar patterns. The solar wind began slowing dramatically. Energetic particles behaved in unexpected ways. Then came one of the mission's most astonishing discoveries. As Voyager 2 approached the boundary separating the heliosphere from interstellar space, its instruments measured plasma temperatures estimated between 30,000 and 50,000 degrees Celsius, hotter than molten lava, hotter than the surface of many industrial furnaces. A temperature that sounds completely impossible for the frozen emptiness beyond the planets. It seemed to defy common sense. How could one of the coldest regions imaginable suddenly contain matter hotter than thousands of degrees? Even more puzzling, why wasn't Voyager destroyed? How could a spacecraft built in the 1970s survive flying through what sounded like an enormous wall of fire? To understand this paradox, we must first abandon the way we think about temperature here on Earth. In everyday life, high temperature almost always means intense heat. Touch boiling water, and you are burned. Approach molten steel, and it radiates tremendous energy. Stand near a campfire, and warmth reaches your skin instantly. Our brains naturally assume that hotter always means more dangerous. But space follows different rules. Rules that challenge our deepest intuitions, because temperature and heat are not the same thing. One measures the average motion of particles. The other measures how much energy those particles can actually transfer. In the near-perfect vacuum beyond the planets, there are astonishingly few particles available to carry that energy. The plasma may be extraordinarily hot, yet it is also unimaginably thin, like a fire made almost entirely of empty space. This bizarre contradiction would become one of Voyager's greatest scientific gifts. It revealed that the frontier of the solar system is not a quiet transition into darkness. It is an active battlefield, a place where the outward breath of our sun collides with the vast environment of the Milky Way. A region shaped by magnetic fields, charged particles, shock waves, and invisible forces operating across billions of miles. Far from being an empty boundary, it is one of the most dynamic regions ever explored by a human spacecraft, and it raises profound questions. Where exactly does the sun's influence end? What creates this mysterious superheated plasma? Why can temperatures reach tens of thousands of degrees without producing destructive heat? What lies beyond this invisible frontier? And what does crossing it reveal about our place inside the galaxy? To answer those questions, we must first understand the force that built this enormous invisible bubble in the first place. A force that begins not at the edge of the solar system, but on the blazing surface of the sun itself. Long before Voyager 2 encountered a wall of superheated plasma at the edge of the solar system, another journey had already begun. It started not billions of miles away, but on the surface of the sun itself. Every second of every day, our star quietly releases an endless stream of matter into space. Invisible, relentless, traveling at extraordinary speeds. Unlike the sunlight that warms our planet in just over 8 minutes, this flow is made of actual particles, billions upon billions of tiny charged fragments racing outward in every direction. This constant outflow is known as the solar wind. Although the name suggests something gentle, like a breeze moving through trees, the reality is far more dramatic. The solar wind is not made of air. It is not a gas in the ordinary sense. It is a river of plasma moving through the vacuum of space, at speeds ranging from about 250 to more than 500 miles per second. At those velocities, particles launched from the sun can travel from Earth to the Moon in just a few minutes. The astonishing question is, why does the sun continuously lose part of itself? Why doesn't its atmosphere simply remain attached to its enormous gravity? To answer that mystery, we must travel upward, beyond the brilliant surface we see from Earth, into one of the strangest regions in the solar system, the solar corona. During a total solar eclipse, When the moon completely blocks the bright disk of the sun, a delicate white halo suddenly appears around it. For centuries, people admired its beauty without understanding its nature. Today we know that this glowing crown is the outer atmosphere of the sun. Yet it presents one of the oldest puzzles in astrophysics. The visible surface of the sun, known as the photosphere, has a temperature of about 5,500 degrees Celsius. Common sense suggests that moving farther away from the heat source should make temperatures steadily decrease. Instead, the opposite happens. The corona reaches temperatures exceeding 1 million degrees Celsius. In some regions, it can climb to several million degrees. Imagine standing beside a fireplace. Now imagine discovering that the air 50 meters away is hundreds of times hotter than the flames themselves. It sounds impossible, yet that is exactly what scientists observe above the sun. This phenomenon is known as the coronal heating problem, and despite decades of research, it remains only partially understood. Several theories compete to explain it. One proposes that countless tiny magnetic explosions, called nanoflares, erupt continuously throughout the corona. Each event releases only a small amount of energy, but together, trillions of these microscopic eruptions may keep the entire corona extraordinarily hot. Another explanation involves powerful waves traveling along magnetic field lines. Known as alpha waves, these invisible oscillations carry enormous amounts of energy upward from the sun's interior. As the waves interact with the corona, they gradually transfer their energy into the surrounding plasma, heating it to astonishing temperatures. Although scientists continue refining these models, one fact is beyond dispute. The corona contains enough energy for some of its particles to escape the sun's gravity entirely. Once free, they accelerate outward into space. That escaping plasma becomes the solar wind. To understand why the solar wind behaves so differently from ordinary gases, we must first understand plasma itself. Most matter on Earth exists in three familiar states: solid, liquid, gas. Heat a block of ice, and it melts into water. Heat water further, and it becomes steam. But if enough energy continues flowing into that gas, something remarkable happens. The atoms themselves begin to fall apart. Electrons are stripped away from their nuclei. Instead of neutral atoms, the material becomes a mixture of positively charged ions and free electrons. This electrically charged state of matter is plasma. It behaves unlike anything we experience in everyday life. Because its particles carry electric charge, plasma responds strongly to magnetic fields. Rather than flowing smoothly like ordinary air, it twists, spirals, vibrates, and forms enormous structures stretching millions of kilometers across space. Lightning is plasma, auroras are plasma, neon signs glow because of plasma. The sun itself is almost entirely plasma. In fact, scientists estimate that more than 99% of the visible universe exists in this extraordinary state. The stars, nebulae, interstellar clouds, even the seemingly empty regions between galaxies contain traces of plasma. From this perspective, the solid world beneath our feet is actually the exception. The universe is fundamentally a plasma universe, but plasma alone does not shape the solar wind. Another invisible force plays an equally important role: magnetism. Deep inside the sun, immense currents of electrically charged plasma constantly churn and rotate. Unlike Earth, whose interior rotates relatively uniformly, the sun behaves differently. Its equator spins faster than its poles. This phenomenon, known as differential rotation, stretches and twists magnetic field lines into fantastically complex shapes. Imagine winding thousands of rubber bands around a spinning sphere. As the sphere turns at different speeds, the rubber bands twist tighter and tighter. Eventually, some snap violently into new configurations. Something similar occurs inside the sun. Magnetic field lines become tangled, compressed, and suddenly reconnect. When they do, staggering amounts of energy are released in an instant. These events power solar flares. They launch giant clouds of plasma called coronal mass ejections, and they continuously feed the solar wind with fresh energy. Yet magnetic fields do more than create spectacular eruptions. They also guide the solar wind itself. As charged particles stream outward, they remain linked to the sun's rotating magnetic field. Because the sun spins roughly once every 27 days, those magnetic lines cannot remain straight. Instead, they twist into an immense spiral winding through the solar system. Known as the Parker spiral, this structure influences nearly every planet. Earth does not simply orbit inside empty space. Our planet travels through an ever-changing sea of magnetic plasma connected directly to the sun. When especially powerful eruptions occur, their effects can reach Earth within days. They disturb our planet's magnetic field. They trigger brilliant auroras. They interfere with radio communication. They disrupt satellites. In extreme cases, they threaten electrical power grids across entire continents. The sun may seem distant, yet its invisible breath constantly shapes the environment surrounding our world. As the solar wind expands farther into space, another extraordinary phenomenon emerges. The particles continue racing outward in every direction. They carry the sun's magnetic field with them. Gradually, they carve out a vast cavity inside the surrounding interstellar medium. Imagine inflating a balloon underwater. The air inside pushes outward, while the surrounding water pushes inward. Eventually, the expanding bubble reaches equilibrium with its environment. The same principle operates on an incomprehensibly larger scale. The outward pressure of the solar wind collides with the thin gas, plasma, and magnetic fields drifting between the stars. The result is an enormous protective bubble known as the heliosphere. It surrounds every planet, every asteroid, every comet, even the distant Kuiper belt. Its exact shape constantly changes as solar activity rises and falls. Rather than forming a perfect sphere, the heliosphere resembles a giant, constantly breathing bubble drifting through interstellar space. Some models suggest it resembles a comet with a long tail. Others indicate it may look more like a crescent, or even a distorted croissant shaped by magnetic forces. Whatever its precise geometry, its scale is almost beyond imagination. Light itself takes well over 16 hours to travel from the sun to the heliopause, the approximate outer boundary of the heliosphere. By comparison, sunlight reaches Earth in just 8 minutes. Every world we normally associate with the solar system occupies only a tiny region near the center of this immense plasma bubble. Without realizing it, humanity has spent its entire history living inside an invisible structure created by our own star. Yet this bubble is far from static. The sun itself follows an approximately 11-year activity cycle. During periods known as solar maximum, magnetic fields become highly tangled. Sunspots multiply across the solar surface. Solar flares erupt more frequently. Coronal mass ejections become increasingly common. The solar wind grows stronger and more turbulent. As a result, the heliosphere expands and becomes more effective at shielding the inner solar system from high-energy cosmic radiation arriving from deep space. Several years later, the cycle reverses. Solar activity declines. Sunspots nearly disappear. Powerful eruptions become rare. The solar wind weakens. The heliosphere contracts slightly under the pressure of interstellar space, allowing more galactic cosmic rays to penetrate toward the inner planets. Earth experiences these subtle changes continuously, although most people never notice them. Space agencies monitor the sun around the clock because our technological civilization depends upon understanding this ever-changing relationship between our star and its invisible bubble. What appears peaceful from millions of miles away is, in reality, a dynamic system constantly breathing with the rhythm of solar activity. For billions of years, this immense plasma bubble has served as Earth's first line of defense. It deflects a significant fraction of the energetic particles racing through the Milky Way. It shapes the environment in which every planet evolves. It creates a distinct cosmic neighborhood carved out by the sun itself. But every bubble has an edge. Eventually, the outward pressure of the solar wind can no longer overcome the pressure of interstellar space. Somewhere far beyond Pluto, far beyond the known planets, the solar wind begins to slow. Its particles pile up. Magnetic fields become compressed. Temperatures rise in unexpected ways. The calm outward flow transforms into something far more violent. This is the beginning of one of the least explored regions in our cosmic neighborhood. A place where the sun's influence weakens, where the galaxy begins to push back, and where Voyager 2 would eventually encounter one of the most extraordinary discoveries in the history of space exploration. On August 20, 1977, a spacecraft no larger than a compact automobile lifted off from Cape Canaveral. 3 weeks later, its twin followed. Their names were simple: Voyager 2 and Voyager 1. At the time, no one imagined they would become humanity's greatest interstellar explorers. Their original mission was surprisingly modest: visit the giant planets, photograph their moons, study their atmospheres, then perhaps continue operating for a few more years before their power systems gradually faded into silence. Instead, they accomplished something extraordinary. Voyager 1 revealed active volcanoes on Io, transforming our understanding of planetary geology. Voyager 2 became the first, and still the only, spacecraft to visit Uranus and Neptune, sending back breathtaking images of worlds no human eyes had ever seen. Mission after mission succeeded beyond expectation, yet the greatest discovery of all lay far beyond the final planet. A destination that had never been part of the original plan, the edge of the sun's invisible kingdom. As the decades passed, the Voyager spacecraft continued moving relentlessly outward. The planets disappeared behind them. Sunlight grew weaker. Radio signals took longer and longer to travel back to Earth. By the early 21st century, each command sent from NASA required more than 16 hours to reach Voyager 2. Another 16 hours were needed for the spacecraft's reply. Every conversation between humanity and its most distant explorer had become a dialogue stretched across nearly an entire day. Yet despite the enormous distance, Voyager never stopped listening. Its instruments continued measuring magnetic fields, charged particles, plasma waves, cosmic radiation. Every byte of data represented information from a region no spacecraft had ever explored before. Scientists believed they generally understood what awaited Voyager. As the spacecraft approached the outer edge of the heliosphere, the solar wind would gradually weaken. The environment would become calmer. Eventually, Voyager would drift quietly into interstellar space. Simple, predictable. Instead, nature had prepared a surprise. Long before Voyager reached the heliopause, the boundary separating the heliosphere from interstellar space, it encountered an invisible region unlike anything previously observed. This region is known as the termination shock. The name sounds violent, and in many ways it is. Imagine a jet aircraft traveling faster than the speed of sound. As it moves, pressure waves cannot escape ahead of it. Instead, they accumulate into a powerful shock wave. Now imagine replacing the aircraft with the solar wind itself. For billions of miles, the solar wind races away from the sun at supersonic speeds. Eventually, however, it collides with the growing pressure of the interstellar medium. The particles cannot continue expanding freely forever. They slow abruptly. Pressure increases. Magnetic fields become compressed. The flow becomes turbulent. This sudden transition forms the termination shock. It is not a solid wall. No spacecraft would ever crash into it like striking a mountain. Instead, it resembles an enormous cosmic traffic jam. Particles moving freely suddenly encounter resistance. Their ordered motion becomes chaotic. Energy is redistributed throughout the plasma. Shock waves ripple across distances measured not in kilometers, but in astronomical units. When Voyager 2 crossed this remarkable region in 2007, NASA expected to observe changes in speed and pressure. Those predictions proved correct, but the spacecraft also recorded something no one had anticipated. The plasma became astonishingly hot. Not hundreds of degrees, not thousands, but tens of thousands of degrees Celsius. Measurements suggested temperatures ranging between approximately 30,000 and 50,000 degrees Celsius. The numbers immediately caught scientists' attention. How could such temperatures exist so far from the Sun? The surrounding environment was one of the coldest places in the solar system. Sunlight there was nearly 1,000th as intense as it is near Earth. Yet the plasma appeared hotter than molten volcanic rock, hotter than the surface of many industrial furnaces. It seemed completely contradictory. At first, researchers questioned the measurements themselves. Perhaps one of the instruments had malfunctioned. Perhaps unexpected electrical interference had corrupted the data. Extraordinary claims require extraordinary evidence. So scientists examined every available sensor aboard Voyager 2. The results remained consistent. Independent measurements all pointed toward the same conclusion. Something remarkable was happening near the edge of the heliosphere. To understand how Voyager measured this invisible furnace, we must remember that spacecraft do not carry ordinary thermometers into deep space. There is nothing for a traditional thermometer to touch. Instead, Voyager measured the behavior of charged particles. Its plasma science experiment, often called the PLS instrument, detected the speed, direction, density, and energy of ions flowing around the spacecraft. From these measurements, physicists calculated the average kinetic energy of the particles. Temperature, in plasma physics, is not determined by how hot something feels. It is determined by how rapidly individual particles move. The faster they move, the higher the calculated temperature. When Voyager entered the compressed plasma near the termination shock, those particles were moving with extraordinary energy. The calculated temperatures reached values that seemed almost unbelievable. Yet another mystery soon appeared. The measured temperatures were actually much lower than theoretical models had predicted. Before Voyager arrived, many scientists believed the termination shock should heat plasma to hundreds of thousands, or even millions of degrees. Instead, Voyager detected temperatures only a small fraction of those expectations. Where had the missing energy gone? That question launched years of investigation. Eventually, researchers proposed a fascinating explanation. The shock wave was not heating ordinary plasma as efficiently as expected because a significant amount of energy was being transferred elsewhere. Into energetic neutral atoms, into accelerated cosmic rays, into particles moving too fast to be measured directly by Voyager's plasma detector. Rather than remaining inside the thermal plasma, part of the shock's energy escaped into an entirely different population of high-energy particles. The discovery fundamentally changed how physicists understood collisionless shocks throughout the universe. The termination shock became more than a curiosity at the edge of the solar system. It became a natural laboratory for processes occurring around exploding stars, pulsars, and even distant galaxies. Meanwhile, Voyager continued traveling outward. Beyond the termination shock lay another vast region known as the heliosheath. Here, the solar wind no longer raced freely away from the Sun. Instead, it slowed dramatically. Its particles became compressed and turbulent. Magnetic fields folded over one another. The plasma grew increasingly chaotic. For more than a decade, Voyager 2 navigated this strange environment. Every day brought fresh measurements from territory never before explored. Scientists began realizing that the heliosphere was far more dynamic than anyone had imagined. Rather than forming a smooth bubble, its outer regions constantly shifted under the influence of solar activity and interstellar pressure. Massive magnetic structures drifted through space. Shock waves generated by powerful solar eruptions propagated outward for years before finally reaching Voyager. The frontier of the solar system was alive. Then, on November 5, 2018, Voyager 2 crossed another invisible boundary: the heliopause. At that moment, several instruments recorded abrupt and simultaneous changes. The density of solar particles dropped sharply. Galactic cosmic rays increased. The surrounding plasma became denser. Magnetic conditions changed. For only the second time in history, a human-made object had entered interstellar space. Voyager 1 had crossed first in 2012. Voyager 2 now confirmed that the transition was real. Yet even after entering interstellar space, scientists continued studying the extraordinary plasma temperatures measured near the boundary. The data challenged long-standing assumptions about how energy moves through nearly empty space. It demonstrated that even in the immense vacuum between stars, invisible electromagnetic forces could concentrate enormous amounts of energy into incredibly sparse populations of particles. This was not fire as we understand it on Earth. There were no flames, no oxygen, no combustion, no glowing inferno surrounding the spacecraft. Instead, it was a fire defined by motion, a fire measured through velocity, a fire that existed almost entirely in mathematics and particle physics. The phrase "wall of fire" is therefore both dramatic and scientifically meaningful. Not because Voyager flew through literal flames, but because it encountered plasma whose particles possessed energies equivalent to temperatures hotter than almost anything naturally experienced on Earth. And still, the spacecraft survived. Its electronics continued operating. Its instruments continued transmitting. Its structure remained intact. How could a machine built nearly 50 years ago pass through plasma measured at tens of thousands of degrees without melting? The answer lies in one of the most counterintuitive principles in all of physics. A principle that separates temperature from heat. A principle that reveals why the coldest places in the universe can simultaneously contain some of the hottest matter ever measured. Understanding that paradox will transform the way we think about space itself. Because at the edge of the solar system, nothing behaves quite the way common sense expects. At first glance, Voyager 2's journey through plasma, measuring between 30,000 and 50,000 degrees Celsius, sounds impossible. Those temperatures are several times hotter than molten lava, far hotter than the hottest desert ever recorded on Earth. Hot enough, it would seem, to destroy almost any material we have ever built. Yet Voyager emerged completely unharmed. Its aluminum structure did not melt. Its electronics continued operating. Its instruments continued collecting data. Even decades later, the spacecraft was still sending faint signals back across billions of miles of empty space. How could this be? Had NASA somehow built a spacecraft capable of surviving inside a furnace hotter than steel? Not at all. The real answer is far more surprising. The problem lies not with Voyager, but with the way our brains understand temperature. On Earth, we almost never separate temperature from heat. The two concepts seem identical because our daily experiences combine them into one sensation. Touch a hot stove, stand near a bonfire, step into boiling water. In every case, a higher temperature also means more heat flowing into your body. Your skin cannot distinguish between the two. It simply feels energy moving from the hotter object into your hand. Because this relationship is so familiar, we naturally assume that temperature alone determines how dangerous something is. Physics tells a different story. Temperature is not the same as heat. Temperature measures the average kinetic energy of individual particles. In simpler terms, it describes how fast atoms or molecules are moving. Heat, however, is something entirely different. Heat is the transfer of thermal energy from one object to another. For that transfer to be significant, two conditions must exist. The particles must be energetic, and there must be enough of them. Imagine a crowded highway. Thousands of cars traveling at moderate speed carry an enormous amount of total energy because there are so many vehicles. Now imagine only a single sports car traveling at incredible speed across an otherwise empty road. Its speed may be extraordinary, but the total energy carried by that lone vehicle is surprisingly limited. Space plasma behaves in much the same way. Individual particles may move extraordinarily fast, corresponding to temperatures of tens of thousands of degrees. Yet there are astonishingly few particles present. The result is a strange kind of fire, one with almost nothing inside it. To appreciate just how empty interstellar space really is, consider the air surrounding you right now. Every cubic centimeter of Earth's atmosphere contains roughly 25 quintillion molecules. That is a number so large it is almost impossible to imagine. Even the cleanest laboratory vacuum on Earth still contains millions or billions of particles within the same tiny volume. Nature, however, creates vacuums that human technology can barely approach. Near the heliopause, where Voyager crossed into interstellar space, the plasma density is incredibly low. Typically, only a fraction of a particle exists per cubic centimeter on average. In some regions, there may be only one ion occupying the volume of a small marble. Most of the space between those particles is simply empty. Imagine standing inside a gigantic cathedral. Now imagine removing everything inside it except a single grain of dust floating slowly through the air. That grain represents one plasma particle. The cathedral represents the surrounding space. This comparison still understates the emptiness Voyager encountered. The spacecraft was not flying through a dense cloud. It was moving through an almost perfect vacuum, sprinkled with tiny islands of energetic particles. Each particle carried enormous kinetic energy, but there were so few of them that they could transfer almost no total heat. This distinction explains one of the most famous misconceptions in astronomy. Many people believe outer space is unimaginably cold because it lacks nearby stars. Others hear about plasma measuring tens of thousands or even millions of degrees and imagine regions hotter than giant furnaces. Remarkably, both descriptions can be correct at the same time. Temperature tells only part of the story. Heat depends on both temperature and particle density. A useful comparison can be found much closer to home. Consider a traditional sauna. Inside, the air temperature may reach 90 or even 100 degrees Celsius. That sounds dangerously hot. Yet people remain inside for several minutes without serious injury. Why? Because air is a poor conductor of heat. Although the temperature is high, the relatively low density of air limits how rapidly energy flows into the body. Now compare that with placing your hand into water heated to the very same temperature. The result is immediate, catastrophic burns. Water contains far more particles packed into the same volume. It transfers heat dramatically more efficiently than air. The temperature is identical. The experience is completely different. The difference lies not in temperature, but in heat transfer. Now imagine another comparison. A steel bar inside an industrial furnace may glow bright orange at more than 1,000 degrees Celsius. Touch it for even an instant, and severe burns occur immediately. Steel is dense. Its atoms are tightly packed together. An enormous amount of thermal energy moves into your skin almost instantaneously. Now imagine replacing that glowing steel with an invisible cloud containing only a handful of particles scattered across an entire room. Each particle still possesses tremendous energy. Yet because so few ever collide with your hand, almost no heat reaches you. This is much closer to the environment surrounding Voyager. The plasma was incredibly energetic. but collisions were extraordinarily rare. The spacecraft simply encountered too little matter to absorb significant thermal energy. This idea seems deeply counterintuitive because our instincts evolved on Earth. Every environment experienced by our ancestors contained billions upon billions of interacting particles. Our brains never needed to distinguish between temperature and density because both usually increase together. Space forces us to abandon those instincts. There is another fascinating consequence of this nearly perfect vacuum. In everyday life, heat moves efficiently through conduction. A hot pan transfers energy directly into your hand because countless atoms continuously collide across the contact surface. In space, there is almost nothing available to conduct heat. Without particles, conduction becomes almost impossible. Convection also disappears. On Earth, warm air rises while cooler air sinks, creating circulating currents that distribute heat throughout the atmosphere. But convection requires fluids. Space contains almost none. The only significant way objects exchange energy in deep space is through radiation. The sun warms Earth because electromagnetic waves travel through empty space, not because hot particles flow directly from the sun to our planet. Voyager experienced the same physical laws. Most of the spacecraft's heating came from sunlight, not from collisions with sparse plasma particles. Ironically, by the time Voyager approached the heliopause, sunlight had become so weak that the spacecraft existed in one of the coldest thermal environments ever experienced by a human-made object. Its onboard heaters were designed to protect delicate electronics from freezing, not from overheating. This apparent contradiction beautifully illustrates how misleading temperature alone can be. Scientists often encounter similar examples throughout the universe. The solar corona reaches temperatures exceeding 1 million degrees Celsius. Yet astronauts flying through the corona, if somehow shielded from the sun's intense radiation, would not instantly vaporize from contact with the plasma itself. The plasma is simply too thin. Likewise, enormous clouds between the stars sometimes contain gas measured at thousands of degrees. Despite those impressive temperatures, they remain among the emptiest regions in existence. The same principle even appears inside particle accelerators. During collisions at facilities such as the Large Hadron Collider, physicists briefly create temperatures exceeding trillions of degrees, hotter than conditions just after the Big Bang. Yet the total amount of matter involved is microscopic. The experiments do not melt the Earth because the overall thermal energy remains extraordinarily small. Temperature alone never tells the complete story. Energy density matters. Particle density matters. Heat transfer matters. This realization transformed scientists' understanding of Voyager's remarkable measurements. The spacecraft had not flown through a conventional wall of fire. Instead, it entered a region where sparse particles had been accelerated to enormous speeds by electromagnetic processes occurring near the edge of the heliosphere. Those particles represented an extreme thermodynamic state, but they did not constitute a dangerous thermal environment for a spacecraft. The phrase "wall of fire" therefore captures only part of the truth. It is scientifically accurate in terms of particle temperature. It is deeply misleading if interpreted as ordinary fire. No flames surrounded Voyager. No blazing inferno engulfed its antennas. No molten plasma washed across its surface. Instead, countless invisible ions sped silently through one of the emptiest environments imaginable. Each carried remarkable energy. Together, they carried remarkably little heat. This distinction has become increasingly important as humanity plans future missions beyond the solar system. Engineers designing interstellar spacecraft worry far more about high-speed dust particles and cosmic radiation than about plasma temperatures alone. A grain of dust striking a spacecraft at tens of kilometers per second can release more destructive energy than trillions of sparse plasma particles drifting past it. The greatest hazards of interstellar travel are often not the hottest environments, but the smallest objects moving at extraordinary speeds. Voyager demonstrated this lesson with remarkable clarity. Its survival was never a miracle. It was a triumph of physics. The spacecraft behaved exactly as the laws of thermodynamics predicted. The universe, once again, proved stranger than intuition. But this raises another question. If the plasma surrounding Voyager was so extraordinarily thin, why did it become so energetic in the first place? What invisible forces accelerated these particles to such astonishing temperatures? The answer lies not in heat, but in a colossal collision occurring across billions of kilometers. A collision between the outward breath of our Sun and the vast ocean of plasma that fills the space between the stars. If the solar system were a nation, the heliopause would be its frontier, not a wall built from stone, not a line painted across space, but an invisible boundary where two immense cosmic forces finally reach a fragile balance. On one side lies the influence of our Sun. On the other, the vast ocean of the Milky Way. For billions of years, these two environments have been locked in an endless struggle. Neither side truly wins. Neither side completely retreats. Instead, they meet at one of the most fascinating frontiers ever discovered by humanity. To understand the heliopause, we must first return to the region Voyager entered after crossing the termination shock. This turbulent zone is called the heliosheath. Imagine a river flowing rapidly toward the sea. As the current approaches the coastline, it slows. Water begins swirling. Whirlpools appear. The once orderly flow becomes chaotic. The heliosheath behaves in much the same way. After the solar wind crosses the termination shock, it is no longer racing outward at supersonic speeds. The violent deceleration has transformed the flow completely. The plasma becomes compressed. Magnetic field lines fold over one another. Charged particles collide through electromagnetic interactions. Pressure rises dramatically. The once smooth stream of solar wind now resembles a stormy sea filled with turbulence. This region stretches for billions of kilometers. Voyager 2 spent more than a decade traveling through it before finally reaching the heliopause. During that long journey, NASA observed something remarkable. The heliosheath was far from quiet. Gigantic magnetic structures drifted through the plasma. Shock waves generated by powerful solar eruptions traveled outward for years before eventually reaching the spacecraft. Every major solar storm launched near the Sun continued propagating across the solar system long after humanity had forgotten it. Even at distances exceeding 100 astronomical units, the Sun still influenced its surroundings. Yet with every passing billion kilometers, the solar wind became weaker. Not because the Sun stopped producing it, but because the particles continued spreading outward into an ever larger volume of space. Imagine blowing air into an enormous room. Near your mouth, the air moves rapidly. Farther away, it spreads out. Eventually, the flow becomes so diffuse that it can barely push against the surrounding air. The solar wind experiences the same fate. Its energy disperses across an immense sphere centered on the Sun. Eventually, another force begins pushing back. That opposing force comes from the interstellar medium. Although we often describe space between the stars as empty, it is anything but. The Milky Way contains an extremely thin mixture of gas, plasma, microscopic dust grains, magnetic fields, and high-energy particles known as cosmic rays. This environment slowly drifts around the galaxy over millions of years. As our solar system orbits the center of the Milky Way at nearly 230 kilometers per second, it moves through this diffuse interstellar material, much like a ship sailing across a calm ocean. The interstellar medium is extraordinarily sparse, yet because it extends across incomprehensible distances, its collective pressure becomes significant. Eventually, it becomes strong enough to resist the outward expansion of the solar wind. Somewhere deep within the heliosheath, these opposing pressures approach equilibrium. The outward pressure generated by the Sun, the inward pressure exerted by interstellar space. When they finally balance, the heliopause is born. Unlike Earth's atmosphere, where pressure decreases gradually with altitude, the heliopause represents a surprisingly abrupt transition. Crossing it does not feel like passing through a doorway. Yet the physical properties of space change dramatically over a relatively short distance. Inside the heliopause, the solar wind dominates. Outside, interstellar plasma takes control. The Sun's magnetic influence weakens. Galactic particles become increasingly abundant. It is here that Voyager 2 made one of its most important discoveries. On November 5, 2018, several onboard instruments detected sudden changes occurring almost simultaneously. The number of low-energy particles originating from the Sun dropped sharply. Meanwhile, galactic cosmic rays increased. The density of surrounding plasma rose significantly. The magnetic environment shifted. Although the direction of the magnetic field changed less dramatically than many scientists had expected, its strength increased noticeably. Taken together, these observations confirmed that Voyager had crossed the heliopause. Humanity had officially entered interstellar space for only the second time. Yet even the phrase "crossed the heliopause" can be misleading. It suggests a thin line separating two completely different worlds. Reality is much more complex. The heliopause is not perfectly smooth, nor is it permanently fixed. It is a dynamic boundary that continuously changes shape. The reason is simple. Neither side remains constant. The Sun itself never stops changing. Every 11 years, solar activity rises towards solar maximum before gradually declining again towards solar minimum. During periods of intense activity, the solar wind becomes stronger. Its pressure increases. Powerful coronal mass ejections launch enormous clouds of plasma into space. Months and even years later, those disturbances finally reach the outer heliosphere. When they arrive, they push the heliopause outward. The Sun's invisible bubble temporarily expands. Later, as solar activity weakens, the opposite occurs. The pressure of the solar wind decreases. The interstellar medium gradually pushes inward. The heliopause contracts slightly. In this sense, the boundary breathes with the rhythm of the Sun, expanding, contracting, never remaining exactly the same. The interstellar medium also contributes to this continual motion. The solar system does not travel through a perfectly uniform galaxy. Different regions of interstellar space contain different densities, temperatures, and magnetic field strengths. As the Sun slowly moves through these changing environments, the pressure surrounding the heliosphere also evolves. Future generations may inherit a heliosphere shaped differently from the one Voyager encountered today. Our cosmic neighborhood is constantly changing. Scientists once believed another dramatic feature might exist beyond the heliopause. A bow shock. The idea seemed reasonable. When a supersonic aircraft flies through Earth's atmosphere, it creates a shock wave. Similarly, researchers expected the heliosphere, moving rapidly through interstellar space, to generate a gigantic bow shock ahead of it. Early computer models predicted exactly such a structure. For decades, textbooks illustrated the solar system surrounded by a powerful shock wave, much like the bow wave of a ship cutting through water. But observations gradually challenged this picture. Measurements from Voyager, combined with data from NASA's Interstellar Boundary Explorer and other missions, suggested something unexpected. The solar system may not be moving fast enough relative to the surrounding interstellar medium to generate a strong shock wave. Instead, it appears to create something gentler. A bow wave. Just as a canoe moving quietly across a lake produces smooth ripples rather than crashing surf, The heliosphere seems to create a broad compression of interstellar material instead of a violent shock. This subtle revision illustrates one of science's greatest strengths. The universe does not care about our expectations. When new evidence appears, theories must change. Even after decades of research, the true shape of the heliosphere continues evolving as observations improve. Computer simulations today reveal astonishing complexity. Rather than resembling a perfect comet with a long tail, some models suggest the heliosphere may look more like a crescent. Others compare it to a croissant, with two enormous plasma jets extending behind the solar system under the influence of magnetic fields. Still, other models remain under investigation. The exact structure remains one of modern astrophysics' active research questions. Voyager's data continue helping scientists refine these competing ideas. Every new observation improves our understanding of how stars interact with their galactic environment. In many ways, the heliopause resembles Earth's shoreline. Stand on a beach and watch the waves. The coastline never remains fixed. Tides rise and fall. Storms reshape the sand. Currents continuously move water and sediment. Yet despite this constant motion, we still recognize where the ocean ends and the land begins. The heliopause behaves similarly. It is a boundary defined not by permanence, but by balance. A balance maintained through countless interactions between plasma, magnetic fields, and charged particles extending across billions of kilometers. Its location today will not be precisely its location tomorrow. Its shape changes continuously. Its motion reflects the changing relationship between our star and the galaxy surrounding it. For Voyager, crossing the heliopause marked the end of one journey, but for science, it marked the beginning of another. Beyond this invisible frontier lay a region humanity had never explored directly, a realm no longer dominated by the sun. Instead, Voyager now drifted through the true environment between the stars. The spacecraft's instruments continued listening, and almost immediately, they began revealing another remarkable surprise. Interstellar space was not as empty, as quiet, or as simple as anyone had imagined. What Voyager discovered beyond the heliopause would fundamentally change our understanding of the galaxy itself. For thousands of years, the space between the stars existed only in human imagination. Ancient civilizations filled it with myths. Early astronomers believed it to be empty. Even after the birth of modern astrophysics, interstellar space remained largely theoretical, a place described by equations rather than direct observation. No spacecraft had ever been there. No instrument had ever measured it firsthand. Then, after traveling for more than 4 decades, Voyager crossed the heliopause. For the first time in history, humanity was no longer studying interstellar space from a distance. We had a witness inside it, and almost immediately that witness began sending home surprises. One of the first changes NASA noticed involved one of the most energetic forms of radiation in the universe: cosmic rays. These are not rays in the ordinary sense. They are extremely energetic atomic nuclei and charged particles accelerated by some of the most violent events in the cosmos: exploding supernovae, rapidly rotating neutron stars, powerful shock waves, perhaps even supermassive black holes at the centers of distant galaxies. Many of these particles have traveled across the Milky Way for millions of years before reaching our solar system. Some move at speeds astonishingly close to the speed of light. Each carries enormous energy. Long before Voyager reached the heliopause, scientists suspected that the heliosphere acted as a protective shield. The outward-flowing solar wind and its magnetic field were thought to deflect many incoming cosmic rays before they could penetrate deeply into the solar system. But no one knew exactly how effective that shield truly was. Voyager finally provided the answer. As soon as the spacecraft crossed into interstellar space, detectors recorded a dramatic increase in galactic cosmic rays. The rise was not gradual, it was sudden. Within a relatively short distance, the intensity of these high-energy particles climbed sharply. At the same time, particles originating from the Sun declined just as dramatically. It was almost as if Voyager had stepped through an invisible doorway. One environment ended. Another immediately began. The heliopause was no longer just a theoretical boundary. Its effects were unmistakable. This discovery confirmed that the heliosphere functions much like Earth's atmosphere. Our atmosphere protects us from harmful ultraviolet radiation. The heliosphere protects the entire solar system from a significant fraction of the energetic particles constantly crossing the galaxy. Without that enormous magnetic bubble, the radiation environment near Earth would be far more hostile. Every planet inside the heliosphere benefits from this invisible shield. Yet cosmic rays were only the beginning. Voyager also entered an entirely new magnetic environment. Inside the heliosphere, magnetic fields are carried outward by the solar wind. Although constantly changing, they remain fundamentally connected to the Sun. Beyond the heliopause, however, the spacecraft encountered the interstellar magnetic field. Unlike the Sun's magnetic influence, this field belongs to the Milky Way itself. It has been shaped by countless generations of stars. Supernova explosions, interstellar turbulence, galactic rotation, and perhaps processes extending across millions of light years. Scientists expected Voyager to observe a dramatic change in magnetic field direction after crossing the heliopause. Surprisingly, that did not happen. The field strength increased noticeably, but its direction changed far less than many theoretical models had predicted. This unexpected result challenged existing ideas about how the heliosphere interacts with interstellar space. Rather than forming a simple magnetic boundary, the two environments appeared to blend together more smoothly than anticipated. The discovery forced researchers to revise computer simulations that had stood for decades. Nature, once again, proved more subtle than theory. Another remarkable surprise involved something almost impossible to see: the density of plasma itself. One might assume measuring plasma density requires collecting particles directly. Yet Voyager's primary plasma instrument had stopped functioning years before it reached interstellar space. Many scientists feared they would never know the properties of the plasma surrounding the spacecraft after the crossing. Fortunately, the universe provided another solution. Powerful solar eruptions launched years earlier continued propagating outward through the heliosphere. Eventually, these enormous disturbances caught up with Voyager. As each shock wave passed through the surrounding plasma, it caused the electrons to oscillate collectively. These oscillations produced faint natural radio frequency vibrations known as plasma oscillations. Voyager's plasma wave subsystem detected these tiny signals with extraordinary precision. By measuring their characteristic frequencies, scientists could calculate the density of surrounding electrons. The method worked because plasma oscillations behave much like the vibration of a stretched guitar string. The tighter the string, the higher its musical note. Similarly, the denser the plasma, the higher the oscillation frequency. Nature itself had created an enormous scientific instrument. Instead of carrying an active plasma detector, Voyager simply listened to the natural vibrations of space. The results were astonishing. The plasma beyond the heliopause proved significantly denser than the plasma inside the outer heliosphere. Although still vastly more rarefied than any laboratory vacuum on Earth, interstellar plasma contained several times more particles than scientists measured immediately inside the heliopause. This sudden increase confirmed that Voyager had truly entered a different environment. The spacecraft had left the Sun's plasma bubble behind. Another important clue emerged from these electron oscillations. They demonstrated that interstellar space is far from silent. Invisible waves continuously travel through the plasma filling the galaxy. Shock fronts generated by solar storms. Disturbances produced by supernova explosions. Magnetic turbulence extending across enormous distances. Interstellar space is not an empty void. It is a dynamic medium where electromagnetic energy flows continuously through extremely thin matter. Every measurement painted the same picture. The galaxy is alive with invisible activity. Perhaps even more remarkable was the opportunity to compare two completely independent journeys. Voyager 1 crossed the heliopause in August 2012. Voyager 2 followed more than 6 years later, in November 2018. Although both spacecraft ultimately entered interstellar space, they did so at different locations and under different solar conditions. This provided scientists with something incredibly valuable. Two separate experiments. Voyager 1 traveled above the plane of the solar system. Voyager 2 crossed farther south. The Sun was in a different phase of its activity cycle. The heliosphere itself had changed shape during the intervening years. By comparing the measurements from both spacecraft, researchers discovered that the heliosphere is not perfectly symmetrical. Its boundary shifts depending on direction. Local plasma conditions differ. Magnetic structures vary. The heliopause resembles a living membrane rather than a rigid shell. No single crossing could have revealed that complexity. Only two independent explorers traveling through different regions allowed scientists to build a three-dimensional understanding of the solar system's outer frontier. NASA had never before possessed such information. In fact, before the Voyager missions, much of what scientists believed about the heliosphere came entirely from computer simulations. Now, for the first time, those simulations could be tested against direct observations collected billions of miles from Earth. Some predictions proved remarkably accurate. Others required major revision. That is how science progresses, not by confirming every expectation, but by allowing reality to challenge our assumptions. Voyager also revealed something deeply philosophical. The boundary between the solar system and interstellar space is not an abrupt transition from familiarity into complete isolation. Instead, the two regions remain connected. Shock waves generated near the Sun eventually reach interstellar space. Meanwhile, galactic cosmic rays continuously push inward toward the solar system. Magnetic fields interact across the boundary. Energy flows in both directions. The heliopause separates two environments, but it also allows them to communicate. The Sun and the galaxy are engaged in a continuous conversation. Voyager simply happened to arrive at the perfect moment to overhear part of it. Even today, decades after launch, the spacecraft continue returning valuable scientific information. Their radio transmitters are incredibly weak. By the time each signal reaches Earth, its power is far less than that required to illuminate a tiny digital watch. Yet, enormous radio antennas belonging to NASA's Deep Space Network can still detect these whispers from the edge of interstellar space. Every bit of information received today was transmitted by machines designed in the early 1970s. Machines carrying less computing power than a modern household appliance. And yet they continue expanding humanity's understanding of the universe. Perhaps the greatest lesson Voyager has taught us is that interstellar space is not an empty destination. It is an entirely new environment with its own plasma, magnetic fields, radiation, and physical processes. The solar system is not isolated. It exists inside a much larger galactic ecosystem. The boundary Voyager crossed is therefore more than the edge of the Sun's influence. It is the place where one stellar neighborhood gives way to another. But these discoveries reveal an even deeper truth. If the heliosphere shields us from so many energetic particles, what role has this invisible bubble played in protecting Earth throughout the history of life? Could the existence of our entire biosphere depend, in part, on this vast magnetic cocoon surrounding the solar system? To answer that question, We must turn our attention back toward home, to the invisible shield that has quietly guarded every planet orbiting the Sun for billions of years. Crossing the heliopause did not mean Voyager had left the solar system. That surprises many people. After all, the heliopause marks the end of the Sun's magnetic influence. Surely that must also be the edge of the solar system itself. But the universe is rarely that simple. The heliopause marks the end of one kind of solar system. The gravitational solar system continues much farther. Even after leaving the heliosphere, Voyager remains firmly under the Sun's gravitational pull. The Sun's gravity extends almost without limit, gradually weakening with distance but never disappearing entirely. Its influence overlaps with the gravity of neighboring stars throughout the Milky Way. So where does the solar system truly end? The answer depends on what we mean by the word system. If we are talking about plasma, magnetic fields, and the solar wind, the heliopause is the boundary. If we are talking about gravity, the story has only just begun. Beyond the heliopause lies a region known as the local interstellar cloud. This is the environment through which our solar system is currently traveling. Despite its name, it is not a dark, visible cloud floating through space. It is an enormous region of extremely thin gas and plasma stretching across dozens of light years. The cloud contains mostly hydrogen and helium, mixed with microscopic dust grains and threaded by weak magnetic fields. Its density is astonishingly low. Only a handful of atoms occupy each cubic centimeter. Yet compared with the near-perfect vacuum inside parts of the heliosphere, even this sparse material represents a noticeably different environment. The local interstellar cloud is part of a much larger structure called the local bubble. Millions of years ago, several nearby supernova explosions likely carved out this vast cavity in the interstellar medium. Their shock waves swept away much of the surrounding gas, leaving behind a region of unusually low density extending hundreds of light years across. Today, our solar system drifts through this ancient remnant. Every planet, every comet, every asteroid, everything humanity has ever known is quietly sailing through the aftermath of stellar explosions that occurred long before human beings existed. Voyager has become our first direct observer of that remarkable environment. But even after entering interstellar space, another enormous frontier still lies ahead. Far beyond the orbit of Neptune, far beyond the Kuiper Belt, there may exist an immense spherical shell surrounding the solar system. The Oort cloud. Unlike the planets, the Oort cloud has never been observed directly. Its existence is inferred from the behavior of long-period comets. These icy visitors occasionally appear from seemingly random directions before diving toward the inner solar system. The best explanation is that they originate from an enormous reservoir of frozen objects orbiting at tremendous distances. If the Oort cloud exists as current models suggest, it may begin thousands of astronomical units from the Sun and extend outward as far as 100,000 astronomical units, or nearly 2 light-years. At those distances, neighboring stars begin exerting noticeable gravitational influence. Passing stars, massive molecular clouds. Even the overall gravitational field of the Milky Way slowly reshapes the distant cloud over millions of years. The Oort cloud is therefore less like a sharply defined shell and more like the fading outskirts of the Sun's gravitational domain. Voyager, remarkable as its journey has been, is still nowhere near this distant frontier. Traveling at roughly 17 kilometers per second, Voyager 1 would require hundreds of years merely to approach the inner regions of the Oort cloud. To cross it completely could take tens of thousands of years. The spacecraft now entering interstellar space has only begun the longest voyage ever attempted. Eventually, if nothing interrupts its path, Voyager will pass relatively close to another star. Not tomorrow, not next century, but tens of thousands of years from now. Voyager 1 is expected to pass within about 1.6 light-years of the star Gliese 445 in roughly 40,000 years. Voyager 2 will eventually approach another nearby stellar neighborhood on a similarly immense timescale. By then, Earth itself may be almost unrecognizable. Human civilization could have transformed beyond imagination, or perhaps disappeared entirely. Yet the silent spacecraft will continue drifting onward, carrying humanity's message into the galaxy. That realization naturally leads to another question. If Voyager can leave the heliosphere, could future spacecraft reach another star within a human lifetime? Today, the answer remains no. Voyager travels incredibly fast by the standards of planetary exploration. Yet compared with the scale of interstellar space, its speed is almost motionless. At Voyager's current velocity, reaching Alpha Centauri, the nearest stellar system, would require approximately 70 years. Human history since the invention of agriculture spans only about 1/7 of that time. Interstellar distances force us to rethink every assumption about travel. The nearest stars are unimaginably farther away than even the most distant planets. Nevertheless, engineers and scientists have already begun imagining the next generation of explorers. One of the most ambitious concepts currently under study is NASA's proposed interstellar probe. Unlike Voyager, whose primary mission focused on the planets, this future spacecraft would be designed from the very beginning to reach and study interstellar space. Advanced propulsion systems could allow it to travel several times faster than Voyager. Instead of taking more than 40 years to cross the heliopause, an interstellar probe might reach that boundary in only a few decades. Its scientific instruments would surpass anything launched during the 1970s. Sensitive plasma analyzers, powerful magnetometers, energetic particle detectors, high-resolution dust analyzers. Together, they could transform the heliosphere into one of the best understood structures in astrophysics. Yet even that remarkable mission would represent only the first step. Scientists are also investigating technologies that once belonged entirely to science fiction. Powerful laser arrays capable of accelerating ultralight spacecraft to a significant fraction of the speed of light. Fusion-powered propulsion systems, antimatter engines, electric sails propelled by the solar wind, magnetic sails capable of slowing spacecraft using the interstellar medium itself. Some of these concepts remain speculative. Others are grounded in well-established physics but await engineering breakthroughs. History reminds us that today's impossibility often becomes tomorrow's routine technology. Only 66 years separated the Wright brothers' first powered flight from humanity's first steps on the moon. The challenge of interstellar exploration may demand even greater patience, but the dream has already begun. Every great era of exploration starts with a single pathfinder. For Europe, it was the first ships crossing unknown oceans. For aviation, it was fragile wooden aircraft. For space exploration, it was Sputnik, Apollo, and Voyager. Future generations may look back on Voyager the way we remember those early sailing vessels. Small, primitive, slow, yet courageous enough to leave familiar shores. Perhaps the greatest gift Voyager has given humanity is not scientific data alone. It has changed our perspective. For centuries, maps ended at the edges of continents. Then they expanded across oceans. Later, they extended to the moon. Today, our maps include the heliosphere itself. The boundary separating our star from the galaxy is no longer an abstract idea. It has become a place visited by human technology. And beyond that boundary stretches an almost unimaginable frontier. Billions of stars, countless planetary systems, vast molecular clouds, invisible magnetic rivers, ancient supernova remnants. Perhaps even worlds where life has followed paths entirely different from our own. Voyager has not answered those questions. It has simply shown us the direction in which the answers lie. the heliopause was never the end of the journey. It was the first milestone on humanity's road into the Milky Way. Somewhere ahead, perhaps centuries from now, perhaps millennia, new spacecraft will follow the faint path Voyager has opened. They will travel farther, move faster, carry more powerful instruments. One day, they may even reach another star. Until then, Voyager continues its lonely voyage through the local interstellar cloud, silently expanding the frontier of human knowledge with every billion kilometers it travels. Its greatest legacy is not that it escaped the solar system. Its greatest legacy is that it proved humanity can begin to reach beyond it. And in doing so, it reminds us that every horizon, no matter how distant, is simply the beginning of the next journey. For centuries, humanity believed the edge of the solar system was easy to define. First, it was the orbit of Saturn, then Uranus. Later, Neptune became the accepted frontier, the last major planet, the final landmark before the darkness beyond. But Voyager taught us something profoundly different. The solar system does not end with a planet. It does not end with Pluto. It does not even end where the solar wind fades away. Instead, its boundary is a living, chain frontier woven from plasma, magnetic fields, gravity, and the constant interaction between our sun and the galaxy itself. The farther we traveled, the less certain the answers became. That is often how science works. Every great discovery solves one mystery while revealing several new ones. Voyager's greatest achievement was not simply reaching interstellar space. Its greatest achievement was changing the very questions scientists ask. Before Voyager, the heliopause was largely a theoretical concept. Computer models predicted where it might exist. Researchers debated its shape. Some imagined a rigid shell surrounding the solar system. Others pictured a comet-like tail stretching behind the sun. But until a spacecraft actually crossed the boundary, every model remained an educated guess. Voyager transformed those guesses into observations. It showed us that the heliopause is not a wall. It is not a sudden cliff where one universe ends and another begins. Instead, it is a remarkably complex transition zone, a place where opposing magnetic fields interact, where charged particles exchange energy, where pressure constantly changes, where the influence of the sun slowly gives way to the influence of the Milky Way. The boundary itself is constantly moving. As the sun grows more active, the heliosphere expands. As solar activity weakens, interstellar pressure gradually pushes inward. The heliopause breathes with the 11-year solar cycle. Its exact position today is not the same as it was 10 years ago, nor will it be the same 10 years from now. This realization changed one of astronomy's oldest assumptions. Nature rarely draws sharp lines. Instead, it creates transitions. Coastlines shift with the tides. Atmospheres gradually fade into space. Galaxies merge without clear borders. Even the edge of the solar system is not a fixed location. It is a process. And despite everything Voyager has revealed, many of the most important questions remain unanswered. Scientists still do not fully understand how energy is distributed throughout the termination shock. Why do some particles become extraordinarily energetic while others do not? How efficiently are cosmic rays accelerated at the boundary? How exactly do magnetic fields reconnect where the heliosphere meets interstellar space? These are not small details. Similar plasma processes occur throughout the universe. Around exploding supernovae, near black holes, inside distant nebulae, across entire galaxies. Understanding the edge of our own solar system may ultimately help explain phenomena occurring billions of light-years away. The heliosphere has become a nearby laboratory for universal physics. Another mystery concerns the interstellar medium itself. Voyager has sampled only an incredibly tiny portion of it. Imagine dipping a single glass into Earth's oceans and attempting to describe every current, every ecosystem, and every coastline. That is roughly the challenge astronomers face today. The local interstellar cloud is only one small region within a vast and dynamic galaxy. How rapidly do plasma density and magnetic fields change from one cloud to another? How do neighboring stellar winds interact? How do ancient supernova explosions continue shaping the environment through which stars travel? The answers remain largely unknown. Future exploration will be essential. That is why scientists are already planning missions that build upon Voyager's extraordinary legacy. One of the most ambitious proposals is the interstellar probe. Unlike Voyager, whose primary purpose was to explore the outer planets, this mission would be designed from the beginning to study the heliosphere and the interstellar medium. Its instruments would be vastly more advanced, its communications far more capable, its observations far more detailed. Scientists hope it could directly measure plasma properties, energetic particles, magnetic structures, neutral atoms, and cosmic dust across the outer heliosphere with a level of precision Voyager could never achieve. Perhaps most importantly, it could test ideas that today remain only hypotheses. How thick is the heliopause? Does its structure vary significantly in different directions? How does the heliosphere respond to changes in solar activity over decades? Where exactly does the influence of the local interstellar cloud begin to dominate? Each answer would refine our understanding of our place within the Milky Way. Yet spacecraft are only part of the story. Much of what we know about the heliosphere has also come from powerful telescopes and observatories that never leave Earth or orbit much closer to home. Space-based observatories monitor the sun's corona, tracking the eruptions that eventually travel toward the heliopause. Radio telescopes detect the faint signatures of neutral hydrogen drifting between the stars. X-ray observatories study energetic processes occurring throughout the galaxy. Meanwhile, missions designed specifically to observe energetic neutral atoms have allowed scientists to construct remarkable maps of the heliosphere from afar. Together, these observatories provide the broader picture. Voyager supplies the close-up view. Like a ship exploring an unknown coastline, while satellites photograph the continent from above, both perspectives are essential. Neither alone could reveal the complete story. Perhaps the most memorable discovery of all remains the one that first captured the world's imagination: the so-called 30,000 to 50,000 degree wall of fire. At first, it sounded almost impossible. How could such extraordinary temperatures exist without destroying a spacecraft? The answer revealed one of the most beautiful lessons in physics. Temperature is not the same as heat. The emptiest regions of the universe can contain particles moving with incredible energy. Yet because those particles are so incredibly sparse, they transfer very little thermal energy. What initially appeared to violate common sense ultimately deepened our understanding of it. The universe did not contradict physics. It revealed physics operating under conditions unlike anything experienced on Earth. That lesson extends far beyond the heliosphere. Again and again, exploration teaches us that intuition is shaped by our everyday environment. The universe is under no obligation to behave according to human expectations. Space is not simply colder, or hotter, or emptier. It is different. Understanding those differences requires observation, curiosity, and the willingness to question assumptions that once seemed obvious. That has always been the essence of science. When Voyager launched in 1977, no one knew whether it would even survive its planetary encounters. No one imagined it would become humanity's first messenger between the stars. Its computers contain less memory than a modern digital wristwatch. Its instruments were designed before the personal computer existed. Yet nearly half a century later, it continues expanding the frontier of human knowledge. Perhaps that is Voyager's greatest legacy, not merely the data it returned, but what it represents. a reminder that exploration is one of humanity's defining characteristics. Every generation inherits unanswered questions from the one before it. Every generation pushes the frontier a little farther. The people who built Voyager understood they would probably never witness the mission's greatest discoveries. They built it anyway. That act of faith in the future is, in many ways, as inspiring as the science itself. Today, Voyager continues its silent journey through interstellar space. Its faint radio signal travels for more than 19 hours before reaching Earth. One day, its power source will finally fall silent. The spacecraft will no longer speak, but its journey will continue. For millions of years, it will orbit the center of the Milky Way alongside countless other stars, carrying humanity's first message into the galaxy. And perhaps, somewhere unimaginably far in the future, another civilization, or perhaps our own distant descendants, will encounter this small machine and recognize it for what it truly was. Not merely a spacecraft, but the first step. The edge of the solar system is no longer simply the place where the sun's influence begins to fade. It has become something far more meaningful. It is the boundary between what humanity already understands and everything we have yet to discover. Beyond that frontier lies not certainty, but possibility. And history has shown that every time we dare to cross such a frontier, the universe rewards us with wonders greater than we ever imagined. Thank you for joining this journey from the heart of the sun to the threshold of interstellar space. If this exploration helped you see our cosmic neighborhood from a new perspective, then Voyager's mission continues to fulfill its purpose, connecting curiosity with discovery across generations. Until our next adventure, keep looking up, keep asking questions, and remember, every horizon we reach is not the end of the journey. It is the beginning of the next one. Thank you for watching.